Right, now we will do the distributions of open times and shut times before going on in the next talk to bursts of openings. What we want to do is to derive, or at least to rationalize, this form as the distribution of all open times and of shut times as well, of course. We saw several times already, I think, this picture of variable open times, often with interruptions, with constant amplitude. And we looked at the distribution of the open times. It looked more or less like this. That's an early experimental example. It's more or less exponential in shape. Well, we shall see soon that in general, the distribution of open times should be a mixture of Ka exponentials, where Ka is the number of open states. We speak of the mixture of exponential distributions rather than the sum of exponential components as you would with a macroscopic current, because since we're looking at a probability density function, its area must come to 1, and we therefore have to talk of a mixture of exponential distributions. I'll illustrate this again later. Now, the fact is, if you read papers about single ion channels, you hardly ever see a distribution that looks like this, an exponential shape, except in the earliest papers where there are some. And that is because we don't normally plot the distribution of open times, rather we plot the distribution of log open times. And that looks like this. It goes through a peak, and most conveniently the peak happens to be at the time constant for the distribution, tau. In fact, more often we plot the square root of that, which has the similar shape and also a peak at tau. Plotting the square root has the effect of making the precision similar in each bin of the histogram. That's why the square root comes in. At an early stage, we found this logarithmic way of plotting was much more sensible, because look at these top 3 graphs. They're all distributions of the shut time for nicotinic acetylcholine receptor channel recording at a very low concentration. And you can see that the shut times went up to, well, 1.5 seconds here. This is a scale which goes from 0 to 1.5 seconds, 1500 milliseconds. And you can see that the long shut times are fit reasonably well with an exponential, except that there's a big excess in the first bin there. And to see what's happening with the short shut times, you have to plot it on a much expanded time scale. This goes up to only 1/4 of a millisecond, and you can see that there are many short shuttings which weren't very obvious from the first plot. So first of all, we thought there were 2 components, but if you look carefully at an intermediate time scale, this goes from 0 to 5 milliseconds, you see that there's a small intermediate component. Now this is tricky because you've got to plot it on lots of different time scales to see if everything's there. But if you plot the same data, but displayed as a histogram of log shut times, we can see a component here with a time constant of about 45 microseconds, a very fast component here. We can also see the slow component with a mean of about 249 milliseconds. a very small number at 1.5 seconds. And we can also see much more clearly this intermediate component. The dotted line fit is with 2 exponentials, and it clearly doesn't fit this middle bit very well, whereas the solid line is a fit of 3 exponentials, and that clearly fits very much better. So that's how the exponential distributions usually look in practice in papers. So now let's get to the algebra. We divide the states into set A, which are open, and set F, which are shut. This mechanism of vacant receptor binding of 1,2 agonist molecules, and in this case we've written it so that it can open in the monoliganded form as well as the diliganded form. So in this case the number of shut states is 2, the number of open states is 2, the number of shut states is 3, and the total number of states is 5. Well, the transition rates between states are defined by the mechanism, and they're laid out in the Q matrix, as we've seen before. We always number things such as the open states, that's the ones in set A, have the lowest numbers, then the shut states have the higher numbered states. And if that's the case, then we can subdivide, partition the Q matrix in this way. This is 2 by 2 because there are 2 open states. This is 3 by 3 because there are 3 shut states, and so on. The top left-hand submatrix, which describes the rates of transitions between open states, is, for example, denoted in that way. And there's one more definition which will be useful for brevity. That is, we define as a G matrix e to the QAAT times QAF. This is time spent in open states, and this is the transition rate from open states to shut states. So this is Ka by Kf in size. The elements of this matrix, which we can call little gij, t in the ith row and the jth column, give the probability densities for staying within the open states for a time t, then leaving for shut state j, conditional on starting in open state I. The details you can find in our 1982 paper. Now, the Laplace transform of this matrix exponential, as we've seen before, is Si minus QAA to the minus 1. And the QAF doesn't depend on time, that's just a constant, so it stays there. And this is a Laplace transform, so we denoted GAF star of S. We change the variable from time to this Laplace variable S. And this Laplace transform gives rise to another very useful matrix. Suppose that we want to know the probabilities of transitions from set A to set F, open to shut, regardless of how long it takes for those transitions to occur. Well, this you can find about by integrating over time. And as we saw in the talk on Laplace transforms, you can do this simply by setting S equals 0 in the Laplace transform. So in this case, when we set S equals 0 in the Laplace transform, GAF star of naught, then it's S, the inverse of QAA times QAF. And here we need to notice something which is quite important for understanding the theory papers. This we denote simply as GAF. Because it's not time dependent, we simply miss off the time in brackets, and so you have to distinguish carefully between GAF and GAF of t. So now let's find the distribution of time spent in open states. The set of all shut states is F. The matrix GAF of t describes the time from the start of an opening through any number of transitions within open states until we eventually exit to a shut state. So the probability density function intuitively should be this, just GAF of t. You've got to then sum up over all possible shut states. This is a unit column vector K, KF by 1, consisting with just the number ones in it, so it sums up the preceding bits over the shut states. And this initial vector, clearly 1 by Ka, we have to find, which we'll do in later. You can write this in other ways. We've just asserted that GAF of t is e to the QAA t QAF, so that's simply inserting that definition. Now we can get it into a slightly nicer form, a form which at least is more directly analogous to the scalar form. If we notice that because the rows of the Q matrix sum to 0, this must be true. And that means that QAF UF is equal to minus QAA UA, and we can write the distribution in that form. And that's neat because it has just the same form as a simple exponential probability function. F of t is lambda e to the minus lambda t, where minus QAA plays the part of lambda, the time rate constant here. The only things that differ in this are the initial vector, which we'll come to, and the fact that you've got to add it up over the various states at the end to make it into a scalar quantity. We can also, once we've got this distribution, find the mean open time most conveniently by using the Laplace transform again. The Laplace transform of this open time distribution, well, the e to the QAA of t bit is SI minus QAA to the minus 1, as we said several times already. The other bits are constant, so they're not affected. Constant in the sense that they don't vary with time. So we pointed out that to find the mean of a distribution, we need to differentiate the Laplace transform of its probability density function with respect to S, change the sign and set S equals 0. Well, to differentiate this thing, we find with respect to S, we find this, just like directly analogous to the scalar differentiation. So this comes out when you said S equals 0 to that, which of course is just that. So the mean of the distribution is the initial vector times the inverse of QAA added up over the A states. So this is exactly analogous to the simple scalar exponential distribution, where the mean is 1 over lambda. This is the inverse of minus QAA, which, so once again, QAA plays the part of the time constant in a simple exponential distribution. Why does this e to the QAAT term keep appearing? Well, the next 3 slides will outline the derivation of it, but if you don't like the maths or you're not interested, you can really skip the next 3 slides. One thing to notice is that for the purposes of macroscopic currents, including noise analysis, for example, we're interested only in the state, open or shut, at time t, and it doesn't matter what happens between 0 and t. So we start for those macroscopic things with probabilities defined like this: the probability that we're in state j at t, given that we were in state I at 0 time. But this is different for single ion channels because it does matter what happens between 0 and t. So to find the lifetime of an open state, the length of time spent continuously in set A, the open states, we need to define a slightly different probability that we remain within the open states from 0 to t, and we're in state j at time t, given that we were in state I at t equals 0, I and j both being members of the open state set. So if these probabilities are elements of a matrix PAA of t, that's the value in the ith row and jth column, then we will show in the next 2 slides that this is just the e to the QAAT. So this is the next omittable slide for the derivation of that result. It's quite tortuous, but it's very characteristic of the stochastic arguments that occur again and again. So this is the probability that we want to define. How do we do that? Well, the transition from state I at t equals 0 to state j at t plus delta t can be via any of the open states, the kth, say. So adding up all the possibilities, we get p at t plus delta t. You see, what we're trying to do is find, we've got p of t there, we want p of t plus delta t here, so we can take the difference between the value at time t and the time delta t, divided by delta t, and let delta t go to 0, because that's how you define a derivative. So this is very often the procedure. So we add up over the k states, the intermediate states, and we get that term, and we multiply that by the probability that we were in state j at time t plus delta t. So the first term is just our original probability, and the second term is what makes the difference, what happens during delta t. So if k is not equal to j, then it's the probability of going from k to j during delta t, which we can write down in this way. This term is familiar to anyone who's done calculus because it's a quantity which disappears as delta t gets very small. If k is equal to j, then this is the probability that we don't move out of k during delta t, which is that. So in matrix notation, we get that. And now the third omittable slide, we can therefore write the differential coefficient of this matrix that we're after can be written in this way. The limit is delta t goes to 0. And we've just discovered that that's equal to that. When we multiply out this square bracket, PAAT minus PAAT disappears, and we're left with this plus this term, which vanishes as delta t goes to 0. So we're just left with dPAA dt equals PAA QAA. And that's what we're left with. And as long as QAA is constant, doesn't vary with time, then the solution of this is exactly like the scalar case. E to the QAAT, this is what we set out to prove. That's called the Chapman-Kolmogorov equation. So we have shown once again that the distribution of all open times is this. We should note yet again how valuable it is to keep track of the shapes of these various matrices. The distribution probability density function doesn't have any matrices in it. It's a scalar quantity. This is a 1 by Ka initial vector, which describes the probability of starting, that an opening starts in each of the Ka open states. That bit is all a Ka by Ka matrix. And the unit vector at the end, vector with all of whose elements are 1, is a Ka by 1, a column vector. So this is all comes out to be a scalar quantity. So now there's two things we need to do to finish this off. One, we want to find out how we calculate this initial vector. And then finally, we want to write out the result in an entirely scalar form with no matrices as a mixture of Ka exponential components. It won't surprise you by this time to see that we do that by using the spectral expansion of e to the QAT. And we want to get it finally into this form, an entirely scalar form. This is an exponential distribution with a rate constant lambda 1, time constant 1 over that, minus 1 over lambda 1 gives you the time constant for this distribution. This is the second exponential component with a different time constant, minus 1 over lambda 2, and so on for however many open states there are. And each of these individual exponential distributions, of course, has an area and rate of 1. So in this mixture, we have to multiply by the area for the first component, the area A2 for the second component. And these areas must add up to 1, so that this is a probability density function, the area of which is 1. So in general, we can write that as a sum of Ka of these ordinary scalar exponential distributions. So first of all, how do we find this initial vector? Well, how does an opening start? It starts by a transition from a shut state, and the transition rates from from each of the shut states to the open states are in the submatrix QFA. This bit has got the transition rates from each of the 3 shut states to the 2 open states. In this particular instance, it looks like that. The shut states are numbered 3, 4, and 5. The open states are numbers 1 and 2 in this particular mechanism. And the transition rates from shut states to open states are to open state 1 are Q31, Q41, and Q51. In this case, that's 0, beta 1, and 0, respectively. So the total transition rate from any shut state into open state 1 is, at equilibrium, are the occupancies, which we stand for the concentrations of the receptor in state 3. That's the equilibrium occupancy of state 3 times the transition rate from state 3 to state 1, similarly for state 4 and for state 5. And the transition rates from any of the shut states to open state 2 are similarly P3 infinity, Q3 2, and so on at equilibrium. But these 2 lengthy looking things are just the 2 columns of the equilibrium fraction in each of the shut states times QFA. That's, of course, a 1 by 2 vector. This is a 1 by KF row vector. This is KF by KA matrix. So the result is 1 by KA. Now, for the purposes of the initial vector, we want to normalize these relative rates so they add to 1. So they're divided by their sum. The rates are in PFA, PFA at equilibrium times QFA. The sum of these things in the numerator we just find by post-multiplying by a unit vector, and that gives us an expression for the equilibrium initial vector. Here's an example. Suppose that PF infinity QFA, the numerator here is 200, 800. These add up to 1,000. That's the denominator there. 200, 800 times 1, 1. That's 1,000. So phi naught is 0.2, 0.8. There's a 20% probability that each opening starts in open state 1, and an 80% probability that any opening begins in open state 2. We can divert for one slide here to notice a rather cool way of looking at the initial vector for openings. It gives the steady state probabilities that an opening state starts in each of the open states. These probabilities must be the same from one opening to the next. So if we look at all the routes that go from start of one opening to the start of the next, regardless of how long these transitions take, then they're given by GAF times GFA, starting in the open state, ending in the open state. These are these G's without a time attached to them are actually the Laplace transforms of G with S set equal to naught, as we pointed out a bit earlier. And that means that the equilibrium vector at the end of one opening must equal to the equilibrium vector at the end of the next opening. The beginning of the next opening. And we can prove that from the fact that, from these relationships, the fact that at equilibrium, P infinity Q equals naught. And that implies these relations. You can work it out for yourself, I hope. So that's the initial vector done. The final thing we've got to do is to use spectral expansion to express the open time probability density function as a mixture of Ka scalar exponential components. So once again, we write our open time probability density function. We then use the spectral expansion of QAAT, e to the QAAT, in terms of the scalar exponentials for the eigenvalues of QAAT times these spectral expansion matrices, these wonderful A matrices, which we described how to calculate. So if we insert for e to the QAAT, it's spectral expansion, we get that. And that implies, because it's got these scalar exponentials in it here, that this is the usual scalar sum of Ka components with areas A and rate constants, eigenvalues lambda. And the areas, when you compare these two expressions, must be given by this. The initial vector times the mth spectral expansion matrix times the mth eigenvalue times minus QAA times QA. You can calculate all of those things directly from the Q matrix. And that's how the areas are calculated. Here's an example of an area with two components, as it would in the mechanism we postulated at the start. This is the open time distribution with the spectral expansion of e to the QAAT inserted in it. So in the case of two components, we'd have the spectral expansion would be that, the scalar exponential of the eigenvalues times the two spectral expansion matrices. If we multiply out the brackets, we get that. So this bit, as we've already pointed out in the more general case, is the area of component 1 times the first eigenvalue of QAA. That's the area of the second component times the second eigenvalue of QAA. And that gives you the entirely general scalar result in the case of two components, which is that. Now, so far we talked only about open times, but actually shut times will give you even more information about mechanisms. So what about the distribution of all shut times? Well, there's the incredible elegance of the matrix notation, because to get the distribution of shut times, all we need to do is to interchange A and F. So the open time probability function, density function was that, with initial vector given by that, everything you can calculate from the Q matrix. And its mean was that, just involved the inverse of QAA. So to get the shut time distribution, all we have to do is swap A for F in everything, and F for A. So rather than QAA T minus QAA, we have QFF T QFF summed over the shut states, and the initial vector has to, as that's 1 by KF, that's KF by KF, KF by 1, so the result is 1 by 1, a scalar. We have to do this swapping trick in the initial vector too, so we call that an initial vector for shut states. This is the initial vector for open states. So we just swap K for A for F in that, and we have that has a mean which is exactly analogous to the mean of the open state. So that gives us a distribution of all shut states. And that ties it up for the open and shut states. Next time we go on for bursts.